So let's get started on the first afternoon session on slide 95. And let's get back to one of our favorite slides, slide 96, which is a thumbnail sketch of growth modeling, and where we use these growth factors to allow for individual differences in growth over time, so continuous latent variables, capturing situations like up here, where we have differences in growth over time. The differences between individuals is to some extent predictable by individual characteristics that are observed, W, but part of the variation in the growth factors is due to unobserved variables, the residuals. You pronounce them as Z or Z, the Greek Z. So the growth factors are to some extent, or to a large extent, unexplained because we don't know what these residual values are. So we're talking about unobserved heterogeneity of the continuous kind. But you can really ask yourself, have we done enough? Is this a realistic representation of data? For instance, if you have Y being reading development for children in kindergarten and first grade, you can ask yourself if individual 3, for instance, really belongs to the same population as individuals 1 and 2. Or if individual 3, with its poor growth rate, is on its way to be diagnosed as having a reading disability problem. That is, does individual 3 belong to a qualitatively different class than individuals 1 and 2, not just a lower residual value, but really belonging to a fundamentally different subpopulation? So if you imagine that you have different subpopulation for individual 3, perhaps the alpha value, the starting point for the intercept, the mean of the starting point, I should say, may be different. It may not be the same for everyone in the population, but it may be different across the two subpopulation of reading in a regular fashion and having a reading disability. And the growth rate may also need to have 2 versions. And that's the idea that we want to capture by growth mixture modeling. And that really seems to fit with many different substantive theories, multiple disease processes in medicine, where it's been a lot of statistical and medical writing about the development of prostate cancer, and we're going to talk about that in a second, and in psychology, multiple pathways of development. We already alluded to the adolescent limited versus life course persistent antisocial behavior, Terry Moffitt's theory, crime curves, which have been studied by Dan Nagin, and alcohol development curves by Bob Zucker and Schulenberg. So here's the case of the medical situation, disease progression, and you have then, in this slide, you have a study of prostate disease where the y-axis is prostate-specific antigen, PSA, prostate-specific antigen, the antigen in the blood, its level, PSA level, and you have four different panels, and you should think about those 4 panels as 4 classes, 4 latent classes, 4 latent trajectory classes. You have the ones for controls, which corresponds to normative development, where with increasing age, we can simplify this example to talk about age here. As age increases, the PSA in the blood increases approximately linearly. And however, if you are in this class, BPH standing for benign prostatic hyperplasia and enlarged prostate, then the increase in PSA is a little steeper over age than for the normals. And then when development is going towards cancers, then the linear development changes into exponential development with rapid growth in PSA. And finally, then, when the cancer has spread, you have an even steeper exponential increase. So this is a medical situation then where you're very interested in, first of all, being able to sort individuals into these different classes. So you want to place a person in figure out the most likely class membership for the person based on repeated measurements of the PSA. And you also, of course, want to estimate, and you want to do that as early as possible. And you also want to estimate the average growth rate and growth function in each of the latent classes. Here's another example, an example that concerns data that I have been working with for several years now. Here are data from UCLA. It's a clinical trial of antidepressants. And in antidepressant trials, we alluded to that earlier, there is a difficulty in assessing medicine effects of antidepressants because subjects tend to have some improvement in their depression already due to a placebo. So it's hard to tease out what the true drug effect is. When a person responds, you don't know if that person, when a person responds, that is, lowers his or her depression due to a drug or when taking a drug, you don't know if that improvement in depression would have happened if the individual had only taken placebo. So trying to disentangle those kinds of treatment effects in the presence of placebo response has been of interest among many psychiatrists and also now among some statisticians, me included. And here is an analysis of the placebo group subjects. What we're looking at is the whole sample of placebo subjects. And the thin lines are the observed trajectories. And the thick line is the average curve. And this is a standard analysis using a standard single-class growth model called random effect repeated measurement model that you could do in any program like SAS-Proc Mixed. The only feature is that we have a piecewise analysis where we have two measures before the randomization and then a number of measures afterwards. So we have a piece of the growth model here and a second piece here. But otherwise, it's a standard model, but we see then that we have a lot of, although the mean captures a general trend on average, we have a lot of heterogeneity, a lot of variability here around that trend. And we certainly do allow for heterogeneity in development, but is there any way to sort individuals into more similar classes? Well, if you repeat this picture, but on a smaller scale, we can ask ourselves, in the placebo group, could we distinguish between those who are responders, placebo responders, and those who are non-responders, those who do not decrease their depression? Well, let's take a look at how we can sort out the heterogeneity in this scatter plot by looking at two different latent trajectory classes. And here they come. And maybe you'll see them more easily on the left screen. So here we have actually done a latent class analysis or growth mixture analysis where we allow for class 1 and class 2 in a totally exploratory fashion. And we see that this class on the left here has some decreasing average trajectory, which comes down much lower than what we will refer to as a non-responder class that has an initial little bit of an improvement, but then stays rather flat and at a higher level around 16 rather than this, which comes down to 10. So you have clarified the picture a little bit from the single class situation up here into using two different classes. And that's an example then that the trajectory shape, the dip here, corresponds to a group of individuals that are qualitatively different from those here. These individuals are affected by the care and empathy of the staff, the nursing and doctor staff that are part of the trial team, and these individuals are not. And you can ask yourself then, well, what if you give a drug, an antidepressant, to these individuals? How will they fare? How will they react? Well, the reaction may be different for those in this class than those in that class. And that's similar to the compliance, non-compliance thinking. And by doing a growth mixture analysis of both groups, placebo and drug group, simultaneously, while allowing for this placebo response possibility, you can better assess what the true drug effect is. And actually, using a larger data set, I actually just got a paper accepted in Statistics in Medicine that I'll be happy to send to you if you're interested, which uses this kind of thinking and also draws on the causal inference that I mentioned yesterday, principal stratification, and it all boils down to a four-class model where we distinguish between individuals who would never respond, would not have a substantial decrease in depression, be they on placebo or be they on drug, and another class, always responders, who would respond to placebo and to drug, and then individuals who would respond to drug only. They would not respond to placebo, but they would respond to drug, and then a class who would respond to drug, to the placebo only, but not to drug. So you have four classes. And we're particularly interested in those individuals who would respond to the drug only. And then you can see how many individuals are in that class and how big of a improvement in or lowering of the depression do you see in that class. So that's what that paper is about. And that's a useful technique, I think, for trials that deal with, that have a strong placebo effect, and that is certainly the case in depression studies, but surprisingly, to me at least, surprisingly also in schizophrenia trials. Here is a general picture then that we saw in the morning of yesterday, and now it seems much easier perhaps. If you look on the right screen, well, you have the same. You have the story on the left. You have longitudinal studies of 18-year-olds that eventually become 37. And you can have hypotheses about different kinds of development over time, normative, escalating, early onset. The thick lines are average curves. Thin lines represent the individual variation around those curves. And we said that for instance, 4 time points, this would be our growth model. We have quadratic growth, I, S, and Q. But we say that there are trajectory classes that affect I, S, and Q. And we now know that C pointing to I, or S, or Q, implies that the mean of I, the intercept, and therefore the mean of I, S, and Q are different. So for instance, if we center at age 18, I is the average level, the mean of I is the average level at age 18. So it would be low for the normative class, a little bit higher for the escalating class, and much higher for the early onset class. So those mean differences will be captured by C pointing to I. And we also would see that C influences S and Q to create these different increases linearly and decreases quadratically. So the growth shapes are captured by C, and we can try to figure out what background variables predict ending up in a certain trajectory class, perhaps family history of alcohol problems, or gender, or age. And X can influence not only class membership, but X can also influence the growth factor values within the class. So if you are a male, for instance, the normative class may have a higher starting point than for females, even within the class of the normative group. Gender may cause higher curves of that quadratic shape type. And then for completeness, we also bring in U, which is then in this case a categorical outcome. And we'll call that a distal outcome. A distal outcome, a consequence of what has gone before. And we're going to argue through two examples that Linda will present that it's preferable to predict distal outcomes. Well, let me put it this way. If you want to predict a distal outcome from the development over time of this y variable, it is much better to predict from C than from IS and Q, because IS and Q interact in very complex ways to influence U, and those interactions correspond to the growth shapes that we have here, and it's the growth shapes that are captured by C, and it's easier then to predict the distal from C than from IS and Q. And we will give examples for how to interpret C on X in a growth mixture modeling context, and examples of how to understand how C influences U in those examples. And apparently we will do that right away.
Okay, so now as Bengt has mentioned, we've left the latent class growth analysis area, and we're looking at GMN, generalized mixture models, or growth mixture models. And the difference, as I mentioned earlier, is that the trajectory classes have variability within each class. So basically, whoops, let me get my thing. So when we looked at LCGA, we said that it was for longitudinal data, and we could have single or multiple items measured repeatedly, and that we had hypothesized trajectory classes that are represented by categorical latent variables. But so what's new here when we go from LCGA to GMM is that the individual trajectories are going to have variability within the classes. So that's the difference. And that difference results in slightly different aims. So the aim of LCGA and GMM are both to estimate trajectory shapes and to estimate trajectory class probabilities. But for GMM, we also want to estimate variation within the classes, and that was not an aim of LCGA. Now, in LCGA, we also wanted to relate class probabilities to covariates, but in GMM, we also want to relate within class variation to covariates. So we're having variability within classes now of the growth trajectories, and we want to be able to explain that variability. We want to understand why everyone doesn't have the same shape within each class, or the same values within each class, although the shape may be the same. And we want to classify individuals. So where we differ is that we want to estimate variation within class, and we want to relate that variation to covariates. So this is how the aims of GMM differ from the aims of LCGA. What we're going to look at first, the first application is mathematics achievement, grades 7 through 10, related to mother's education and home resources. And this is taken from LSA data longitudinal study of youth. And it's a national sample with 846 observations. And now these math achievement items are continuous variables, so our dependent variables are continuous. We talked when we did LCA and other categorical outcome analyses about how we would compare models. And we used BIC, Tech 11, Tech 14, and also Tech 10 for categorical. Now, when we have continuous outcomes, we can't use Tech 10 anymore. We don't have univariate and bivariate tables. We can still look at BIC, looking at a low BIC or a minimum in BIC. And we can still look at the low Mendel-Rubin likelihood ratio test and the bootstrapped likelihood ratio test. But in addition, we can look at residuals, class-specific comparisons of model estimated means, variances, and covariances versus posterior probability-weighted sample statistics. So residuals observed minus expected for continuous outcomes. And we can also look at Tech 12 and Tech 13. Tech 12 gives us class mixed residuals for univariate skewness and kurtosis, and Tech 13 tests whether or not that skewness and kurtosis could be generated by the model. And if we don't want to be able to reject the null hypothesis that the skewness and kurtosis came from the model estimated skewness and kurtosis. So that's something else that we can look at now when we move on to continuous outcomes. And as we have discussed over these last 2 days now, the interpretability and usefulness of the latent classes, we have to consider theory to really determine whether or not they're meaningful. So we look at the shapes and we see whether they make sense. And we look at the number of individuals in each class. And as we mentioned earlier, there's really no rule about that. But sometimes very small classes, it's difficult then to predict the variation within class because the covariates may not vary within the class. We look at the number of estimated parameters. We're always wanting the most parsimonious model that we can have. The substantive theory will drive the trajectory shapes. And then we can also look at auxiliary variables in the terms of predictive validity. So for example, we may have a distal outcome, and we can see, do the classes relate to the distal outcome as one would expect? And that's a form of predictive validity. And that can also help us see whether or not the trajectory shapes really make sense. Classification equality is, as always, the posterior probabilities, the classification table and entropy. That hasn't changed. And I'm not sure what the last bullet is, so I'm going to ask you to say something about that. It's not important. Okay. And here is the model that we're going to look at. So we have, I mentioned that we're going to be looking at math achievements. So we have math in grades 7, 8, 9, and 10. And we have a linear model. So we have two growth factors, the intercept growth factor and the slope growth factor. And we're going to regress those two growth factors on mother's education and home resources. And now that we have continuous outcomes, you note that we have the arrow representing the residual. So we estimate a residual variance for each outcome variable because they're continuous. Now, we have our categorical latent variable over to the left of the oval, pointing to it. And what that says is basically we're going to let everything vary across classes. All free parameters in the model we're going to allow to vary across the classes. And that would be in the regression of I and S on mother's education and home resources. The default in Mplus is to hold those regression coefficients equal across classes, but we're going to allow those to vary along with the intercepts. And the residual variances will also be allowed to vary across classes. Now here's a table, much like the tables we've been looking at for the last couple of days, where we've trying to determine the number of classes for the model on the left screen. We have calculated a one-class model, a two-class, or estimated a one-class model, a two-class model, and a three-class model. Now the one-class model is just simply a conventional growth model. So if you run in Mplus a conventional growth model without type equals mixture, and then you run type equals mixture classes equals C1, then you will get the identical results because they're the very same. So the one-class model is the same as a conventional growth model. Now here's a situation where we finally are able to actually use the statistics to determine the number of classes in a pretty clear way. So we see that we have an increase from 1 to 2 classes in the log likelihood, fairly large and not so large going on to 3, so that would point to 2 classes. Our BIC actually has a minimum at 2 classes. It goes from 24098 down to 23928, and then back up again to 23959. So that also points to 2 classes. If we look down at Tech 11, we see that we have a probability greater than 0.05 for 3 classes, which points to the K-1 or 2 class model. The first time we see the multivariate p-values for skewness and kurtosis come from Tech 13, and the first time they become larger than 0.05 is with 2 classes. So here's a situation where everything very clearly points to 2 classes. A unique situation in real data analysis, I would say. And actually, I think I'm going to put this on both screens and talk about it over here. So there's quite a lot of controversy. There has been quite a lot of controversy over the last several years about whether LCGA is better than GMM, and there have been many articles written and a lot of opinions exchanged. So for this example, we want to take a look at, first of all, the model at the top is LCGA. So the growth factor variances and covariances are fixed to 0. And what we have here is we're looking at model fit using BIC. And so BIC is on the y-axis, and the number of classes is on the x-axis. And if you look at BIC for the LCGA model, you'll see that it decreases, and it continues to decrease, but it never actually hits a minimum. And this is one thing that happens with LCGA models, is BIC continues to dip but doesn't really hit a minimum, doesn't give you a good idea of how many classes there are, or because of not having variation within classes, it looks for more classes than are needed, really. The classes are just variations on the theme. Now, in this situation, the second one, we have growth factor variances and covariances, but we hold them equal across the classes. So we allow variability within the classes, but we require that variability to be the same across classes. So growth factor variances and covariances are held equal across classes. And you can go down here and see that for this one, it decreases and it seems to have a minimum at 2. When we then go on to the next situation, which is down at the bottom here, we then allow the full GMM model where the growth factor variances and covariances are both free and unequal across classes. So each class has a different growth factor variance and covariance, or variances and covariances. And here you see we hit a minimum and pointing to 2 classes. The last thing on the diagram is a model, the same model we looked at with free variances and covariances across classes, but we've added covariates. So that changes where it lies, but not the idea that the BIC is still decreasing with a minimum pointing to 2 classes. So that confirms what the other things that we looked at, and it shows the 2 classes. Now the point here is that the LCGA model may be the correct model in many situations. And I think in certain types of data, like criminology data, this often is the case. But if it isn't the case, which I think it isn't in many other fields, you can test it by doing a GMM model. If you do a GMM model and there's no variability within classes, then the growth factor variances for the classes will be estimated at 0, or at a value that's not significantly different from 0. So you can then, if you see that, make the more parsimonious LCGA model by fixing the growth factor variances and covariances to 0. But if you just do an LCGA, you don't have an opportunity to test whether the assumption of no within-class variability is true or not. So that's sort of our take on that, if you've heard about the controversy. So it's always better to test an assumption than to just make the assumption and make it not testable. Okay, so now this is a summary of the results, and to see how things might differ if you do a conventional growth model versus the GMM, where you have within-class variability. So here's the results from our model. We have 2 classes. Class 2 is at the top. A Y represents the math achievement, and then time on the x-axis. So Class 2 at the top here are people who started out higher in math and had a stronger slope, so they grew faster. The conventional growth model's here in the middle. The bottom is Class 1, and these are individuals who started lower. They're more heterogeneous. You see more variability within the class, and people seem to grow at a slightly slower rate. So we have a more homogeneous group, starts higher, grows faster. A more heterogeneous group starts lower and grows somewhat slower. So if we look at the relationship, if we look at the regressions of the intercept and slope growth factors on the covariates in both the conventional and the GMM model, we see that there's different relationships found. And let me go here, because I always know you can't see the bottom from there. So at the bottom, we have our conventional single-class analysis. Here's the intercept regressed on mother's education and home resources. The slope regressed on mother's education and home resources. The asterisk represents significance. So in the conventional single-class analysis, we would conclude that where individuals start in the growth process is affected by mother's education and home resources. And here the slope on, that represents how they grow. And so we're saying that how they grow doesn't depend on mother's education, but it does depend on home resources. So this is what we would conclude from the conventional analysis. If we instead look at the GMM results, Class 1, the lower class here, where they start is dependent on mother's education, but not home resources, and how they grow is dependent on home resources, not mother's education. Whereas the high class, where they start, the intercept growth factor, is dependent on both mother's education and home resources, but how they grow, the slope growth factor, the variability in that is not explained by either of the covariates. So as we said earlier, the aim in GMM, or one of the aims, is to estimate with in-class variation and explain it. So, this is a simple example, but it shows the idea that if you ignore the heterogeneity in your data, then you make different conclusions about the importance of covariates than you would if you instead have a GMM model where you have within-class variation that you can explain by different covariates. So we are starting here with the results. And then we'll take a look at the input that was used to get the results and also the output, so I can show you in the output where we got the results. So for your own information, if you wanted to create a table like this. So here's the input is on the left screen and the right screen. Okay. So I don't think there's actually anything on this screen that people aren't familiar with. We'll use observations, which we really haven't explained, but we took a subset of the data. So if you have your full data set and you only want to analyze certain individuals, like females or something, you can use the use observations option for that. And we probably haven't seen the missing option. Missing equals all, which says for all variables, 999 is the missing value flag. So I think there's nothing new here where type equals mixture. But the most important thing, I think, is the model command. So we said that we were going to allow everything to vary over classes. So in the overall, you see we have the growth model specified, intercept slope slash math 7 at 0, math 8 at 1, math 9, and math 10. You'll note we don't have at 2 and at 3. So that's another advantage of having the time scores be parameters in the model. You can actually estimate them. So they don't have to be fixed. You can have free time scores, and that's what we're allowing here. We're allowing the time scores. We're going to fix math 7 at 0, math 8 at 1, but we're going to estimate the time scores for math 9 and math 10. We don't feel that it's totally linear. A model would fit the best, so we'll estimate those. Then we regress the intercept and slope growth factors on the two covariates, mother's education and home resources. We do that in the overall part of the model command. But then, as the default, those regression coefficients are held equal across groups. So in the class-specific model command for class 2, we specify intercept slope on mother's education and home resources. By mentioning them in the class-specific part of the model command, it relaxes the equality. So now they won't be held equal. And the same for the residual variances of math 7 through math 10 and the intercept and slope growth factors. Those would be held equal as the default. So we want to relax the equality and let those be unequal across classes, and also the covariance between the slope growth factor, or the residual covariance in this case, between the slope growth factor and the intercept growth factor would also be held equal across the classes as the default. And the Mplus defaults are based on two different decisions. One, what's most often done in practice. For example, in factor analysis, fixing the first factor loading to 1. That's our default to set the metric of the factor instead of fixing the factor variance at 1. So that's sort of one of the defaults. That's what's done in practice. In this situation, the equalities across classes are done because when everything's unequal across classes, it can be more difficult in some cases to estimate the model. So we give, as the default, it's a model that's easier to estimate, and then you can relax the equalities as needed. But every default in Mplus can be overridden. There's no default in Mplus that you can't change, other than the fact if you change something that makes the model not identified, then that's not allowed. So that's the input. And I'm just going to go through some of these screens. So we have our regular output and just point to the things that are most important. And mainly that's where you get. So here, we talked about this yesterday. And here's the Tech 12 output. And here we have the observed skewness. And the observed skewness is actually from the full sample. And the estimated skewness is mixed over the classes. And observed minus expected are the residuals. So here you have, that's Tech 12. And Tech 13 then gives you the p-values that we saw when we looked at the summary table I gave at the beginning. So we have a multivariate skewness test, and then a multivariate kurtosis test. So here's our test of skewness, and you can see the p-value is greater than 0.05, and two-sided kurtosis test, p-value here. Actually, let me put the summary table up so I can then put where it comes from the output over there. I think that might be helpful. That's 107. Okay, so you can see down here, we have the 0.34 and the 0.10 from the left screen. And those values were greater than 0.05 at the second for the class 2, indicating that the class 2 solution would be the correct solution. Somebody calling? All right, so now over on that screen we have the results. So, and these are for class 1. And you can see that we have all of the intercept growth factors, factor loadings fixed to 1. And for the slope, for math 7 is fixed at 0, math 8 is fixed at 1. And remember, we just said we were going to estimate math 9 and math 10. And you can see that they were estimated at 2.422 and 3.588, rather than the values of 2 and 3 that we would have fixed them to for a totally linear model. What we're interested in here and what we used in the final results that I showed you are the regression of the intercept and slope growth factors on mother's education and home resources. And the significance patterns were taken from the last column there. And just to mention this, I don't think it ever hurts, but these are linear regressions because the intercept and slope growth factors are continuous. So the estimates are linear regression coefficients. And then we show the residual covariance between the intercept and slope growth factors and the residual variances and the intercepts. And let me mention, this is a growth model for a continuous outcome. So the parameterization of that growth model is to fix the intercepts of the outcomes at 0 and let the intercepts of the intercept and slope growth factors be free. I don't know if you remember, but for the categorical growth model, the parameterization was to hold the thresholds of the outcomes equal, have the intercept growth factor, intercept or mean be fixed at 0, and estimate the intercept or mean for the slope growth factor. So that's why these are 0. It's a different parameterization that we use for continuous and categorical. And the reason we do that is really when we have ordered polytomous variables, it makes for a less restrictive model to have equalities of thresholds across time rather than fixing them all to 0. Okay, so that was class 1 results. We have the same results for class 2. One thing we did hold equal across classes were the estimated time scores for the growth model. And then at the bottom here are the significance patterns that we used in that final picture where we showed the conventional model at the bottom and class 1 and class 2 at the top. And okay, and then the residuals that we get, we have, okay, so the residuals are the model estimated. So it's observed minus expected, as always. And so here's the model estimated, and the observed are not exactly observed because they're posterior probability weighted observed. You know, since we have multiple classes, we can't just get observed for the overall. So we have to weight using the posterior probabilities. So we have model estimated, and here's the residuals. But observed, which are used with model estimated to obtain the residuals, are posterior probability weighted. And then we have our model estimated covariances. And this is, so just to ground this a little bit, so the residuals are something we can use to assess model fit when we have the continuous outcomes. And here are the residuals for the covariances. And as you note, none of them are particularly large. And then I think it's time for you.
So on this slide, 122, you have the progression of papers that I've been involved in writing on this GMM topic. And the latest in that sequence is the 2008 paper at the top, which has a series of examples and also is the most complete description of the statistical techniques behind the modeling. Actually dealing not only with mixtures, but also with multi-level aspects of growth mixture modeling. Now, Linda's example there for the LSA math talked about relaxing the default specification of free variances and covariances for the growth factors, but held equal across the classes, to letting them be different across the classes. In actual analysis, you would first use, I think, the default of class invariant variances and covariance for the growth factors. And then you would do a plot, and we have these plot command where you can plot the estimated mean curve for each class and the individual trajectories for individuals who are most likely to be in that class. And when you do that plotting, you could see if one or two classes seem to have less of a very individual variation around the mean than others. And for those classes, you may want to go back then and modify the model so that you allow that class or those classes to have their own factor, growth factor covariance, variance-covariance matrix. So you take it stepwise with the help of those plots. I think it's a good idea. You don't want to go for the most general model right away. So the default setting is pretty well chosen, I would say. And the default setting being that only the growth factor means or the growth factor intercepts are varying across the classes. I think that's a good, those are the ones that vary the most. That's a good starting point. Now, it does make a difference in terms of classifying individuals. First of all, whether or not you allow growth factor variances or covariances, which the LCGA model does not and the GMM model does. It makes a difference in the classification, and also makes a difference in the classification if you let the growth factor variance covariances be equal or different across classes. So you should expect to see differences there, and you would want to proceed cautiously, and typically you would not free as many parameters as we do in this LC example. For instance, typically the INS, the growth factors regressed on covariates, would not necessarily be different across classes, but the default again is to hold them the same. So now let's talk a little bit more about this LCGA versus GMM, modeling without versus with random effects, to get a further, deeper insight into that. And I think this then relates very strongly to the relationship between LCA and FMA that we talked about yesterday. So latent class analysis corresponding, being the analog of LCGA, and factor mixture analysis being the counterpart to GMM. And maybe I'll do that on the big screen here. So this really corresponds to debate that is taking place in the criminology methodology literature. And it started out in that literature with Dan Eging coming up with working with latent classes and the SAS-proc TRAJ for trajectory analysis, working within the LCGA framework. And that became quite prominently used in criminology, analyzing these crime curves, trying to look for types of criminal behavior and development. Now on the other side, though, already in the literature, in the methodological literature, there was the random effects approach to longitudinal modeling. And one example is Steve Raudenbush and the Raudenbush and Breich book and the HLM program in the US, which is quite different. Raudenbush would represent unobserved individual differences or unobserved heterogeneity by continuous random effects variables, as is done in standard statistics, repeated measurement modeling, whereas Nagin would represent unobserved heterogeneity by latent classes. So there was a discussion in the literature of criminology by Sampson and Laub which approach is most suitable, and I think they were critical of the Nagin approach. There were some troubled waters here that you could see in the literature. But there was a bridge built over this, I think, by growth mixtures, and which helps in deciding between these two approaches. And actually, my assistant to help me with this picture, she's so young that she didn't even know about this Simon and Garfunkel song. But now she does. So, but there was some fraction here in the air, some lightning strikes here. Dan Egin published his book on his ideas, and he was quite critical of the growth mixture modeling. And I guess I've never written a reply, but you have the implicit response here. Here's how I see the situation. I think Raudenbush views the world as top right. Where are we? Top left on the right screen. That is, you have, everything is continuous heterogeneity. That is, you have variation in the intercept, variation in the linear slope, variation in the quadratic slope, and that's all you need. the observed variation in the trajectories can be covered by that individual variation that is orchestrated by the random effects. So it's a single class random effect growth model of the standard kind. Nagin, on the other hand, does not deal with individual variation, but talks about trajectory classes. So he sees the world in this simple way, that you have these trajectory types, and once you're in a certain type trajectory, every individual in that type of trajectory has the same probability of a certain trajectory development. Now, my worldview has always been very complex. That is, life has been very complex for me, from my eyes, I should say. So I think of there being types of behavior, but quite a lot of variation within each type. And in fact, variation so that for some individuals, it's hard to decide whether or not they're high normative or they are early onset people. And for some individuals, the classification is not great, but there is enough individuals of each type, each of the three types, to talk about, in this case, three different classes of trajectories, but allowing for the within-class variation. That's how I see it. My a priori notion of what the data might be like. And so this corresponds to the LCA, FMA, and factor analysis discussion that we have. The leftmost representation would correspond to what we talked about in factor analysis, only using continuous latent variables. The rightmost would be latent class analysis, where we have three classes, and within each class we have conditional independence. And in this case, the conditional independence here is for variables, the repeated measures. So we're saying that, say, two consecutive outcomes over time are independent for individuals within a certain normative class. And my feeling is that that's often unrealistic, because when we do the analysis, there's so many factors influencing your response, like time-varying covariates. We only talked about time-invariant covariates, say in mother's education. That doesn't change over time necessarily. But time-varying covariates left out in the model can influence both yt plus 1 and yt, even within a normative class, which would tend to make repeated measures within the class be correlated. And this model does not allow for that, whereas when you allow for factors within classes, as you do in GMM and as you do in FMA, you can allow for an estimate within class non-independence. So it's exactly the analogous situation as in the LCA, FA, and FMA context. Now, you can argue all day long about which model is best here, and you can have the philosophical debates, but that's why we have statistics, where we let the likelihood decide, and clearly, statistically, HLM and LCGA are special cases of GMM, and as Linda said, you can actually test for which model is appropriate. You can see if the factor variance-covariance matrix for the growth factors has significant elements or not. So to illustrate that, let's take a look at an example which is in that 2008 book chapter that I mentioned earlier. By the way, that 2008 book chapter, which page is that on? The slide, the 2008, the previous further readings set? Page, well, let's revisit that, 1, 2, 3. We were talking about this paper. It's actually, I should mention that while I remember it. It is a chapter in a very good book on longitudinal data analysis from 2008, written by a team of, or edited by a team of excellent statisticians. And it has a lot of good chapters on longitudinal data analysis having to do with growth, survival, missing data, and combinations thereof. So I really recommend that you buy that. It's a little bit on the statistical side, true, but it is overview style. It's not heavy in terms of statistical matters. Now, let's look into a typical criminology data set. We had one earlier, that's Nagin's classic Cambridge data, the 408 boys that Linda talked about. But now we have that's only 400 individuals and hard to make decisions on such rare events. Here we have the Philadelphia crime data, which is part of that chapter. And it is for about 13,000 individuals. And we talk about annual counts of police contacts, and individuals with more than 10 counts in any year were deleted. It's a very small set of individuals. And data are combined into 2-year intervals. And now we're going to get back into drawing on all the knowledge that we have accumulated so far, including Poisson regression and zero-inflated Poisson regression from yesterday morning. So we talk about zero-inflated ZIP, growth mixture modeling of counts. So the annual counts, number of police contacts, 0, 1, 2, etc. And the outcome variable is the count variable U for time point T for individual I. And here's how you can write the ZIP modeling. U can be 0 with probability pi. That you might write, that's a 0 class. These are the non-criminals in this case. These are the individuals who would never think of committing a crime. So that's a 0 class. So people are going to have 0 and 0 alone if they are a member of that class, and that has probability pi. And notice that that probability is time dependent. It can vary across time. You can become a criminal after a while, and certainly varies across the individual as a function of, say, background variables. But the other people who belong to the class who do commit crimes at a given time point follow a Poisson distribution for the number of counts. So this then gives that mixture at 0 that I was talking about. Again, for those of you new, if you observe a 0 crimes, it could be because you are not a criminal or because you are a criminal. This is very simplistically put. You're a criminal, but you just happen to not commit crimes in that particular time interval. So this is a way to capture the overrepresentation of 0 crimes that Poisson could not handle alone. So it's 0 inflated Poisson. And then you have the log rate equation, for the Poisson people, the criminals. And in this case, it's intercept, linear slope, and quadratic slope. Time is age here, represented by A. The notation varies widely in this field, so you just have to get used to going back and forth between notational schemes. And the intercept, linear, and quadratic slopes are written without covariates here, but just a mean alpha and a random residual with a certain variance, where these have are assumed to have a normal distribution and be possibly correlated. And then we note also that in Mplus, regarding this inflation, the probability of being a non-criminal for person I at time point T is the probability that U sharp or U number, or actually in Sweden they call that fyrkant, square. I don't know if they call it square in German, but we call it a number sign. So U number Ti is equal to 1, where U number is a binary latent inflation variable. So it's a binary variable, but it's unobserved. You don't know if you are a criminal or not a criminal. And U equals 1 indicates that the individual is unable to assume any value except 0. So U number 1 equals 1 corresponds to being a non-criminal. It's a little bit complex there, but you can handle it. Now, if you go through different modeling alternatives, as it's done in that chapter, we have the growth mixture models contrasted with the latent class growth analyses. And I wanted to do that just to see in Nagin's own application area how these models differ. Fine, Linda talked about LC, but that was for continuous outcomes, and there clearly GMM beats LCGA, but continuous outcomes is not the typical case in criminology. So let's work with this count outcome, which is the typical kind of outcome. So you look at the one-class GMM, which Linda pointed out is a model that is conventional growth model. And the variables are correlated due to the random effect, the growth factors alone. And we look at log likelihood, number of parameters big, and we also look at number of significant bivariate residuals. Contrast that with the two-class GMM, likelihood goes up by about 200 points. True, we add 4 parameters, so let's look at big. Well, it's an improvement. Number of residuals goes down a little bit. 3-class GMM, you increase the likelihood even further, but at the expense of 4 more parameters. So, but nevertheless, the big goes down, a low big is good, so, and the number of residuals also goes down from 4 to 1. And a 4-class GMM, even better, slightly better big, and 0 significant residuals. Now compare that to LCGA, where we do not allow for, in the LCGA, we're saying that there are no residuals here. There are no residuals. Their mean is 0, and by saying that the variance is also 0, they vanish. So there is no individual variation around the 3 means at all. So what happens then? Well, big is for 4, even for 4 class is likelihood even for 4 class is worse than the likelihood for 1 class GMM. And that's reflected by the worse big value here. And you see that even when you go up to 8 classes, you are not doing as well as you do even with only 3 classes GMM. 3 classes GMM has a lower big than even 8 classes LCGA. So that's an illustration of that by not allowing for within-class variability, LCGA tends to need more classes to capture the correlations among the variables. Here's what it looks like if you choose the 3-class zip. So if you don't go down to 4 but stay with the 3-class, which already looks pretty good in terms of the number of significant residuals, here's what it looks like. For a very large sample, you have the normative development, essentially non-criminal activity, perhaps a little bit of a tendency at 16. And then you have the adolescent limited development here in class 2. About 16% show adolescent misbehavior around 16, 17, but calm down by age 20. And then you have the life course persistent criminal behavior for class 1 of about 20% of the individuals. So there's an illustration of being able to have random effects in the context of a mixture longitudinal analysis, even when the outcome is count. And here's how you do the analysis on slide 131. You specify that the outcome variable is a count, and I stands for inflated, which says that you do a 0 inflated Poisson, 3 classes. You need to use integration. You want to have a quick processor because this is a large sample. You have 3, I believe you have 3 random effects, intercept, slope, and quadratic, and 3-dimensional integration is slow, so we go down. I'm going to talk about numerical integration at the very end of today when you're totally exhausted. You cut down on the integration points per dimension from the default of 15 to 10 to make it a little faster, and you'll still be okay. You do 50 and 5 random starts, and you can monitor the progress of the 4 optimizations, the 4 because the process equals 4 on your screen, by an interactive control file that you can go in and stop some failing random starts. So you can sit there and really drive the computer and have a lot of fun. And then you have the model, which is very simple. The growth model is quadratic, and we center at the first time point here, which you can do. And this reflects the equidistance between the ages that we had observations. So there's nothing new there. The estimates are latent class 1. You have the means of the growth factors, which govern the shape that we plotted. And here you have the number variables, y. I would call them u now, but it doesn't matter. These are the inflation factors. These corresponds to logits reflecting the probability of being in the class that doesn't commit crime. So in this case, we estimate for each time point an inflation factor here, and letting that be free, those inflation probabilities, which have to do with the probability of not being a criminal at any of the at the given time points. Sometimes you may want to put a growth model structure on that inflation part, which you could add to the growth model for the regular output. You can have an IS and Q for the Y10 sharp 1 and Y12 sharp 1. So a second growth model, putting a structure onto this. And I'll give you some references for how to learn how to do that. But in this case, it's unstructured probabilities, and we let them be free. You see the variances here for the growth factors. They're large estimates relative to the standard errors, and in that sense, significant values, and therefore, you would not want to fix them at 0. And latent class 2, you have a new set of growth factor means. And in class 3, yet another set of means. Now, if you want to read more about this at a peaceful pace, a former postdoc of mine, Frauke Kreuter, from somewhere in Germany, but now at the University of Maryland, we wrote a paper together in Journal of Quantitative Criminology, and we played on this theme of trying to bridge multi-level, which is the HLM random effect approach, and the group-based approach, which is Nagin's name for LCGA, using growth mixture modeling, bridging the two. And we go through all of the steps of considering how to do that model in a fairly applied fashion. And corresponding to that, there's also a chapter in this book, Advances in Latent Variable Mixture Models, which you may want to get. If you're interested, it's a print-on-demand type of enterprise. So you can go onto our website, and you will find a web address for getting that book, and it has some good chapters in it. And again, this example, the Philadelphia crime data, appears in this book chapter by me and Tihamer Asparoho. Now, we should also mention some caveats here for growth mixture modeling, some risks. This modeling works quite well for distributions that you can imagine arise through a mixture of normals. We're always working with a mixture of normals here. If we say that we have a continuous outcome, it's a mixture of normals. So for instance, if you look at this situation here, top left, this bar you can ignore, it's the missing data bar. But here's the distribution. This is actually having to do with aggressive disruptive behavior in the fall of first grade. You have a distribution here and a little bit of action here. And then for spring, you have a peak here, a second peak, and a little bit there. This could be captured by, say, a 2 or 3 class normal distribution. But if you have a situation which you have at the bottom, for instance, bottom right here on slide 138, again, ignore the missing data. When you have a preponderance at 0, it's very hard to work with a mixture of normals. So here would be a case where you would work with a 2-part model. So a 2-part model would be particularly suitable for that case. whereas you don't have that piling up at 0 at the top picture here. So that's one thing to think about. And two-part modeling then being handled by this diagram that we've already covered. The other aspect that you should think about is, whoops, 141. And this one you have to think about hard, because if you see a non-normal distribution like this, there could be two ways to think about that. One is that it comes about because you have a mixture of, say, two normals. If you mix two normals together in proportion 75%, 25%, with slightly different means, perhaps slightly different variances, but you don't even need slightly different variances. If you mix them together, the distribution will look like that. So two normals with different means and even with equal variances will look like this, which is a log normal distribution, very skewed distribution. So you can ask yourself, do the data that we see here come about due to mixing two normals, or is really the data generated by a single class that is log normal? And there was a big debate about that, referred to in the McLachlan and Peel book, already on page 14, blood pressure debate. So we're talking about blood pressure here. And one group of individuals thought of hypertension as a disease. So those who had high blood pressure were in a special class distinct from low normal blood pressure, whereas others would argue, no, there's not two qualitatively or substantively meaningful distinct classes. There's just a continuum over all of these values. A little bit like the psychiatric debate about dimensions and categories. Comes back in many shapes and forms and is reflected in the statistical modeling here. And then Bauer and Kern wrote a 2003 article in Psych Methods where they took this debate further in the longitudinal setting, whereas this was in the univariate setting, and warned people that the latent trajectory classes that you find could be due to non-normality in the outcomes only. A non-normal distribution where you try to fit normal mixtures to it will give you more than one class, perhaps two classes. It doesn't imply that the classes are substantively meaningful. That you have to decide by other means. So that's one caveat. If you can easily get classes, but are they meaningful? Are they useful? Is something that you have to ask yourself. And we're going to talk about several ways to assure you of whether or not these are meaningful. We're going to do that with the help of a couple of examples. And I don't know if we should take a break now or questions now.
Right.
Yeah. So why don't we stop there and let there be time for questions and answers, and then we'll get into these applications for the rest of the day.
First of all, do you have an input for the two-part model?
Question is, do we have an input for the two-part model? Not in these handouts, but they would be in the topic 3 or topic 4 handout that sits on our website.
Okay.
Don't we have that in the user's
And we have it in the user's guide as well, yes, right, which is also on our website.
Okay, one more question about the 3 classes, the life course persistent criminals, the adolescent misbehavior, page 130.
130?
Page 130.
There is the normal class, and it should have a slope of almost 0. But this is class 3, right? The normal class.
That's class 3, yes.
And the results are the slope is 11.36 and significant.
Could you get to
that's the page
output corresponding to that?
Maybe
it is on 130.
135.
135, okay.
Here.
Yeah. So class 3 here is looking at these values, yes. Right. Well, it is a scale of this that even though it is 11 and minus 14, all it does is raise this a little bit. So it's a matter of scaling. 11 looks very big, but in this context, it's a very small rise that you see. Yeah. So it's hard to interpret the absolute values of this.
Can I ask you to go to slide 126?
126.
Oh, 126, okay. Oh, that's that weird thing.
Hit it again a couple of times.
Very interesting discussion, but my challenge is the growth mixture model. How much of an impact on the power do all the additional calculations have? How much more power do you need? How much larger sample to be able to do these calculations?
Yeah, no, that's a good question. What extra power do you need? What extra sample size do you need to go from, say, this to this? This LCGA has become quite popular because not only does it require somewhat lower sample sizes, but it also is much quicker to compute. So there's a tendency among us to like a methodology that is fast and simple. But that's not the right decision criterion. We should first investigate whether or not it's suitable for the data. But say that it is. Say that it is. I haven't systematically investigated how much less, say that you are in this situation, how much smaller can the sample be as your variances for your growth factor decrease? I have not looked at that. There's a study that somebody can do through the Monte Carlo simulations. So it's true, if it really is the case that you have very little within class variation, you could probably get away with a smaller sample, but I don't know how much smaller. It's not that many parameters that are added, however, so I wouldn't think that you buy that many, you save yourself that many observations. That would be my prior.
I can tell you one thing positive about GMM. A grant went out from our institution with latent gold as a model of choice for the analysis, and of course LCGA. The grant reviewers were very critical of the fact that LCGA does not take into account within class variation, and they called it a black box. And the grant was rejected. It was one of the reasons that they were very critical about, but it came back with a very critical review.
I couldn't get the critical review of having within class variation or not having it.
For putting in the grant that they were going to use latent gold, which uses LCGA.
Oh, I see. So critical of the LCGA approach, the grant was rejected. Well, there are people in both camps, and I think one should have an open mind and let the data and the statistics decide.
Exactly. If there's no
But it's good to
variation,
hear.
you'll find that.
Yeah.
So there are a big group of people who use latent gold.
Yeah.
And I have to fight all those people. And I'm one of the sole survivors of
Don't fight them. Let the statistics decide.
Exactly.
I don't know if this is is or has been a hot debate here in Europe, but in the U.S., in some camps, it has been somewhat heated. It's amazing how people can be so passionate about statistics. It's a little patent place.
Exactly.
All right.
I have a question about page 116.
116?
How would I interpret the estimates of the slope?
I'm sorry.
Could you say that again, please?
How to interpret the estimates of the slope?
Oh, here. Here?
Yeah.
The estimated time scores?
Yeah.
So is that what you're asking, how you would refer to the estimated time scores?
How
Yeah,
to
because you
interpret it.
set
how to
them free in the
interpret them.
model.
Well, Linda was saying that if you fixed it at linear, it would be 2 and 3. And so what you have to then consider is
It's like
the step from 1 to 2.4 is a little more than 1 to 2. So that means, the way to translate that is, it means that there's an acceleration in math performance at that point. I think it's between 8th and 9th grade, because there's a lot of math teaching in 8th grade in US schools. So a little bit of an acceleration between 9 and 10, between 8 and 9, but then the step between 9 and 10 is back to about 1. So it sort of goes like this. So it's almost like an S-shaped learning curve. That's how you would interpret it. Would you agree?
Yes.
Okay, and then also a question on page 107.
107?
How can I use the multivariate skew p-value and the Kurtosis p-value? How do I interpret them? What are they good for?
So about the p-values for multivariate skew and multivariate kurtosis.
So, well, basically, you look for the first place where you cannot reject the null hypothesis that the basic, you hate it when I say this, but I'm going to say it, that the skewness and kurtosis come from the data, or the model.
Yeah, so
But anyway.
this says that the probability that the model generated skewnesses of the kind of the size that we see in the sample is 0.34. So this is the likelihood that the model can generate skewnesses of the size that you see in the data. That is, you cannot reject that this model has generated the data with respect with respect to the skew and with respect to the kurtosis. So when you have a mixture, you get a mixture of normals gets very skewed, as we saw in the picture. So you get a certain skewness, that's a third order moment, and a certain kurtosis, the fourth order moment, that's different from a normal. And here we're asking, does the model generate skewness and kurtosis that is seen in the data? And we cannot reject that the model does generate the proper skewness and kurtosis seen in the data when we have two classes. So already with only two classes, do we capture the skewness and kurtosis in the data? That's how I would.
And how would you interpret the 0.05 then? For 3 would be going away from the rejection?
I would not. Once you have quote unquote accepted the two-class model, you shouldn't go further and even consider those.
I have a question about something on page 133.
133.
There are means for the 10 measures for Y10 to Y24, and I'm not sure what they really mean, how to interpret them. And I mean, the first couple of estimates go down and then they go up again, but the means of the actual class go up first and then go down. So maybe you could say something on what they are and why they can be freely estimated and are not fixed.
Yes, okay. So if you just shift it around so you can read it here. So this has to do with the inflation part. So let's go over this again. So the question is about this inflation parameters in the loaded scale here for the different time points. So we're saying in Mplus, the probability of ut equals 1 has to do with these inflation parameters, saying the probability that you're not a criminal at a certain time point. U equals 1 indicates that the individual is unable to assume any value except 0. So U equals 1 has to do with not being a criminal. And here is the logit corresponding to the U equals 1 probability. And we know that when the logit is high, that is greater than 0, the probability is high. So high logit is high probability, low logit is low probability. It's the opposite for thresholds, but let's forget them right now. So this says that the probability is high for an individual not being a criminal at age 10, but then it increases, it's much higher. The probability of not being a criminal at age 12 goes down relative to up here, and goes down further. That is, you become more likely to be a criminal as it increases up to 16, but then the probability of being a criminal decreases again. And in this case, but here then at 22 and 24, the load is very low, so probability of being a non-criminal is very low. Let's see, am I saying that right? Yes, minus 15 is a low logit, so it's a low probability of being a non-criminal is what that says. And fixed at minus 15, which is, the fixing probability is, I switched it into thresholds too. So a low load is a low probability here. So this is a probability that gets close to 0 when you fix the load at minus 15. So in any case, these logits have to do with are the loaded counterparts to the probabilities pi. Probabilities pi having to do with being a non-criminal. Now I don't know if you want to interpret them that separately. I know that some programs don't even print them out, but they do help in making the Poisson model fit the data better.
Over here, next over here. No,
go ahead.
After you.
You have it here.
No, we're not going to run the mic around.
Could you show page 96 and 100?
96?
96 and 100.
101.
One what?
101.
101.
If W or X are background variables and
Is the value of what?
background variables.
Say that again?
Background variables, such as gender and
I don't hear the word.
background.
Oh, background.
A W or X in the other one.
So
If they are not time invariant variables such education or income, how do you model this? How can you include such variables into these models?
variables like education.
Education changes over time,
okay.
or
I see
income.
So you're talking about a covariate here, which we illustrated only the simplest case where the covariate doesn't change over time, like gender. And your question is about covariates that change over time. So we call them time-varying covariates. And you just add boxes here, boxes that point directly to the y variables. So you would have a box for first time point pointing to y1, another box for education at time 2 pointed to y2, etc. So the time-varying covariates would be included in level 1 here, adding to it. So we just talked about the most simple case of the time-invariant covariates. So, but they will be included here, a set of time-varying covariates influencing their own specific y at a certain time.
And I think that's shown in example 6.12 in the user's guide, or if not, close to 6.12.
Yeah, so in the user's guide, you will have examples of time-varying covariates.
And day 3.
In topic 3.
Topic 3.
I want to ask something again about 133 to 135 and 130. Yeah, maybe it's good to have 130.
135?
Yeah, it's about the 3-class Philadelphia thing. So the estimates, if I understand it right, they don't make any sense at all. Because the estimates means for S and Q for latent class 3 are roughly the same as for latent class 1. but their
Jackie?
profiles are really different.
Do you want me to go backwards?
Let's see.
So the profiles are on page 130.
The picture on 130, and you're saying that the estimates for class 3 are similar to those of class what?
Yeah, so that's class 3 is on 135 and class 1 is on 133.
Class 1 on 133.
Yeah, and then for
So
slope
class-
and
so one
quadratic.
It could be that Jackie did them backwards. So we have
Oh,
2,
okay.
12, 15.
So I don't know how to interpret them,
So
or should
you're
I just
comparing
have
class 1 to class 3, is that it?
Yeah.
So
okay,
we
so
have
let me look at it for 2 seconds then.
12 and 15, 11 and 14.
Are you saying that these values are similar? If
So
we're-
yeah, so to me, like S and Q, they look quite similar, and but if I look at the picture, they're like completely different.
So
You're right,
what-
because the one class is down low and the
Yeah.
one class is
So
up
the
high.
one is just flat, and the other one is like kind of quadratic.
Can you
Where's
say
the-
the picture page again?
130.
130.
Oh, I'm going the wrong way.
There it is.
So class 1 and class 3. Class 1 and class 3. It looks like there's a mix-up of the class numbering then. Let me
That's
just
class
take a look
2.
here. Class 1 is the high class. Class 2 is a,
So it looks like this is the high class.
yeah.
It looks like there's a mistake in the,
Yeah, could be
whoever
a,
typed this output.
could be
in.
a flipping of the classes here. I couldn't say offhand.
But they should match.
Okay.
So I would suspect that there's a mistake in this output.
Almost 0. That's the same question as I asked.
Yeah, it was
Right.
related to your question. Yes, right.
Yeah, so it looks to me like,
We'll check that.
So normally you should be able
let
to
me make a
interpret
note.
them.
Yeah, we'll make a note of
Yeah,
that.
no, it should make sense.
I should
And-
say, we put up, after we do these training sessions, we always go back and improve the handouts and then post corrected handouts. And then we work with that corrected handout next time we teach, and we find more errors and we correct that. So you have a page on the website where you have the latest handouts. So when we come home, we'll post a new revised version. We also have to post the version that we videotaped, because that's what you had in front of you. So we'll have 2 versions going on at the same time. But we'll check up on that to see
Yeah.
if there's a problem, what the problem is.
Okay, I have, although I know it's not the introductory session now, and basic questions were to be asked in the beginning, but now I have a very basic question.
Good.
When we compare different criteria, such as big, we say that we look for big that is decreasing.
Decrease.
Yes.
right.
Decreasing, yes. And in case we find a minimum, it's fine. But there were a couple of cases you mentioned when you said, well, it's decreasing, but it's not decreasing a lot. What is a lot?
I don't think there really is a definition of a lot. I think it's, you get a feel maybe more through doing a lot of data analysis. And once again, sometimes you've seen in the examples we've just shown, we don't always hit a minimum. And so then when you can't make a decision based on BIC or any of the other statistical techniques that we recommend, then you have to look to the classes and take a look at them and see what makes sense, you know. So if it keeps getting lower, but it's not a lot, well, is the difference between 3 classes and then 4 classes, which is not a lot, how do those look? Does it make sense to interpret the extra class, or does it not? So then it comes down to being subjective, much like EFA.
Well, that's what I usually tell my students when I teach this, and they don't like this answer.
We'll tell them they have to get used to it, because that's life.
Here are 2 other answers. One is that when BIC doesn't find a minimum, or when there are only small differences in BIC by adding more classes, typically I would argue that you're in the wrong ballpark in your model. There's another model where assuming that there is a signal in the data, which there may not be, you know, the way you collect your item, not you, but others, There may not be clear signals, and therefore maybe you have to go to another model, like going from LCA to FMA, going from LCGA to GMM. Another answer is that there have been attempts by Bayesian statisticians to quantify what a big difference is. There's a paper by Cass and Wasserman, which Nagin in his work refers to, and Cass and Wasserman, and I forget the year, but they try to quantify in qualitative terms, small, medium, large. But that again builds on a theory that comes with its own assumption, Bayesian analysis, and I don't know how much it's worth. But there are some attempts in the literature to quantify that you may want to give to your toughest students. Okay, more questions?
Does it look like we're ready for a break? Why don't we see you back then in 20 minutes?
Okay, see you back at 3:30 then.